Hello viewers, my name is Dr. Ajay, Associate Professor, Institute of Aeronautical Engineering College, Hyderabad. So my name is Dr. Ajay, Associate Professor, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. And today's topic is a discussion of a tutorial question bank of arrays and measurements. So this is a topic belongs to the module 4 of the course Antennas, Waves and Propagation. So let us start our session today. Plot the E-field pattern of the arrays of two isotropic point sources having equal amplitude lambda by 4 spacing and phase difference of 90 degrees. So plot the E-field pattern. So arrays of two isotropic sources given, we need to draw the radiation pattern by finding the E-field. So what is the amount of electric field produced by two isotropic sources? First we need to find out. After that, we can draw the radiation pattern based upon the equation of E. The spacing is given as lambda by 4 and the phase difference of 90 degrees. So for arrays of two point sources, we are having an equation E is equal to 2 E naught cos psi by 2, where psi is equal to beta d cos theta. So plus alpha, and the alpha is taken as 0. Why? Because it is given as equal amplitude. So the phase difference we are going to indicate here. The alpha value phase difference is given as 90 degrees. Now let us find out the value of D is given as lambda by 4 here, and E is equal to 2 E naught. Suppose let us say psi. What is the value of psi? Psi is equal to 2 pi by lambda. The value of D is lambda by 4 into cos theta plus 90 degrees. Now from this equation, lambda get cancelled, 2 2's get cancelled. So this is pi by 2 cos theta plus 90. Now what is psi by 2 here? Psi by 2 is equal to pi cos theta plus pi by 2. Now from this equation, cos psi by 2 is equal to cos of pi by 2 plus pi cos theta. So cos 90 plus theta is equal to minus sine pi. So here beta is equal to 2 pi by lambda into d is equal to lambda by 4. It is beta d cos theta. So beta d cos theta means it is lambda by 4 cos theta plus pi by 2 here, 90 means. So here lambda get cancelled, 2's get cancelled. So this is pi by 2 cos theta plus pi by 2. So this equal to psi by 2 means you will get pi by 4 cos theta plus pi by 4. So we are getting here the value as cos of psi by 2 is equal to psi by 2 is equal to pi by 4 cos theta plus pi by 4. This is psi by 2. So let us apply E is equal to, you will get 2 E naught cos of psi by 2 we know. So for this 2 E naught cos of psi by 2 means pi by 4 plus pi by 4 cos theta. So cos of pi by 4 plus cos theta. Now for normalizing this as the magnitude as 1, the maximum amplitude is taken as 1. So simply we can write it as E is equal to, cos of pi by 4 plus pi by 4 cos theta. Now for different values of theta, let us substitute value of theta as 0, as 90 or 135, 180, 270 and 360. We are going to find out the value of E here for different values of theta. Suppose if we substitute the value of theta here, this is theta and this is E. Let us substitute theta as 0 here. If the theta value is 0, we will get 0 here. Here theta is 0. Now again the theta value is 90, you will get 1 by root 2. Again if you substitute the 120, theta value is 120, you will get 0.94. Suppose the theta value is 150 degrees, so you will get 0.99. Similarly, if you substitute 180 as theta value, then you will get the value of E as 1. Now from this data in the table, we need to draw the radiation pattern. So here, let us assume here theta is equal to 0 degrees here, and theta is equal to 90. Here theta is equal to 180, and here theta is equal to 270 degrees. So here theta is equal to 0 is equal to 0 here. So when theta is equal to 0, the value of E is 0 here. Now when theta is 90, E value is 1 by root 2 here. Assume the magnitude as here, the point as up to here 1, this is 1, and this is 1, and this is 1 on the x-axis. So here this is the 1, this distance is 1 unit, and this distance is 1 unit, this distance is 1 unit, and this distance on the y-axis is 1 unit here. Now for 90, it is given as 1 by root 2. So 1 by root 2 means it will come approximately here. This is 1 by root 2 here. And for 120, so here this is 120 degrees. It is how much the value is taken as 0.94. So 0.94 you will get approximately here. And for 120, for 150, so for 150 you will get approximately here. This is for 150. So like this we need to draw for 180 also it is 1 here. So for 180 this is 1 here. So like this you need to draw the, you need to join all those points, you need to mark all the points and join all those points. You will get the radiation pattern like this. So this is the E field pattern of array of two isotropic point sources having equal amplitude and lambda by 4 spacing and a phase difference of 90 degrees. So similarly you can, this is the radiation pattern we are having. So based upon this value here, so for 0 it is 0, 90 is 1 by root 2, 120 is 0.4, for 150 is 0.994, and for 180 degrees it is 1 here. And similarly you can also try this problem. So plot the E field pattern of the arrays of two isotropic point sources having equal amplitude, lambda by 2 spacing and phase difference of 90 degrees. So from the equation of E is equal to 2 E naught cos psi by 2, and where psi is equal to beta d cos theta plus alpha. So we should find out the value of E here. So beta means 2 pi by lambda. Here the d value is taken as lambda by 2. So in the previous problem we have taken the d as lambda by 4. So when the spacing is increased here, the spacing is increased to lambda by 2. We are observing extra minor lobe here. We are observing one extra minor lobe. So the spacing, there is a limitation on the spacing between the elements of an array. So if the spacing is increased, between the elements is increased, though the bandwidth is increased, the minor lobes will be increasing more. The minor lobes are increased more and more when the spacing between the elements is increased here. So we need to find the value of theta and E here. For 0, 60, 90, you can take any number of theta values. You can also take as 0 as theta as 0, 30, 45, 60, 90, 135, 120, 180, 270. And you should need to find out the values of E here. And as per the data in the table, we need to draw the radiation pattern. So we know that this is a x-axis represents theta is equal to 0 degrees, and the y-axis represents theta is equal to 90 degrees here. Now draw the radiation pattern of two isotropic elements fit in phase space lambda by 2 apart by pattern multiplication. So here two elements are given, 1 and 2. This is now forms an array whose spacing is given as lambda by 2. Whose spacing is given by lambda by 2. So by the principle of pattern multiplication, so what the pattern multiplication says is an array of two elements, the pattern multiplication, the resultant pattern is given by the product of the pattern of the individual element to the group pattern of the total number of elements in an array. So the pattern multiplication is given as the resultant pattern is equal to unit pattern multiplied with group pattern. So unit pattern is nothing but the pattern produced by each individual element or any individual element. The pattern produced by any individual element of an array, we call it as a unit pattern. And the pattern produced by the two elements, any two elements or a group of two elements or a group of four elements, the pattern produced, we call it as a group pattern. So which we call it as a group here. Here the group is 1 and 2. Here the unit pattern is one element. That is the individual element either 1 or 2. So either 1 The pattern produced by either 1 or 2 we can take in this example. Also the group pattern means it is 1 and 2 here. Suppose if I am taking 4 elements, 1, 2, 3 and 4. So we can take, this is spacing is lambda by 2, this is lambda by 2 and this is lambda by 2. Let us assume here these 4 elements are separated by lambda by 2 and lambda by 2. And let us combine these 2 elements as 1 unit and these 2 elements as 1 unit here. The total length is, it is lambda here. And this is assumed as A and this is B. So here the resultant pattern for this is given by the unit pattern of A or B multiplied with group pattern of A and B. Group pattern of A and B. So like this we can determine the relation pattern of 2, 4, 8 or 16 number of elements spacing between the lambda by 2 pattern. But if we want to find out the pattern multiplication, we need to know the relation pattern of any 2 elements separated by lambda by 2 or any 2 elements separated by the lambda by 4 or any 2 elements separated by lambda or 2 lambda. So it's a pattern multiplication is a method to determine the relation pattern just by inspection. Just by inspection means we need to know the relation patterns of lambda, 2 lambda and lambda by 2 to draw the relation pattern of 8 elements or 16 elements or 32 number of elements. So now let us see the relation pattern here. So we know that from basic equation E is equal to 2E1 sin theta cos psi by 2 here. So for the 2 elements here. So this is the produced by the individual element. E naught is equal to E1 sin theta here. As the elements are here horizontal here. Here the elements are placed horizontal, the relation pattern will be like this. The relation pattern is like this. Hence, the relation is maximum at 90 degrees here. The relation is maximum at 90 degrees. Hence, we are taking the function as sin theta. If we consider the dipoles as vertical, the relation pattern will be like this. It is 0 and this is 180. Then we can take as E1 cos theta. Then we can take as E1 cos theta in this case here. So E naught is equal to E1 sin theta for 90 degrees as the relation is maximum in the 90 degrees. So E is equal to E2 E1 sin theta cos psi by 2. So if we normalize this function, we will get E is equal to sin theta and cos psi by 2. Now what is this sin theta? This sin theta represents the pattern produced by the individual element. The pattern produced by 1. And what is this cos psi by 2? It is the pattern produced by 1 and 2 elements of an array, which we call it as this is the group pattern and this is the unit pattern. This is the unit pattern and the group pattern here. So here you can see here the sin theta means the pattern of individual isotropic source and cos psi by 2 is the pattern of array of 2 isotropic point sources. The pattern of array of 2 isotropic point sources. So for sin theta we need to draw the relation pattern here. So for sin theta you can see here the relation pattern will be like this. So for different values of theta here. So for sin theta, if you substitute theta value is 0, substitute theta is equal to 90, theta is equal to 180 and theta is equal to 270. So we can see here the direction of 90 and 270 it is 1 here. So the relation is 1 and it is 1 here. And for cos psi by 2 also we need to find out the value of psi is equal to beta d cos theta. And this is 2 pi by lambda. This is 2 pi by lambda into lambda by 2 into cos theta. Lambda get cancelled, 2 get cancelled. So this is psi by 2 is equal to pi by 2 cos theta. So E is equal to, we get pi by 2 cos theta. So for this we need to draw a table and we should find out the value of theta and E. So for different values of theta we should find out 0, 90 and 180. We should find out the values of E here. Find out the values of E here. And if you draw the relation pattern, you will get for cos psi by 2, this is the relation pattern we are getting here. So here if we multiply these two, here, this is maxima and this is maxima. So maxima multiplied with maxima, we will get maxima whole square. That means the relation pattern will be in the same direction. Some amount of relation pattern, we can draw a bigger relation pattern here, like this. So this is maxima and this is maxima. So maxima multiplied with maxima will get maxima square. Hence we can represent a bigger relation pattern as the resultant pattern of array of 2 elements. as an array of 2 elements here. So this is how to draw the relation pattern of 2 elements. Similarly, the same concept can be extended for 4 elements and 8 elements also. So for the 4 elements we are taking here, 4 elements here. So we are going to combine these 2 elements as one unit pattern and these 2 elements as another unit pattern here. Assume this as A, assume this as B here. Let us join these 2 points here. So here the spacing is lambda by 2, here the spacing is lambda by 2, here the spacing is lambda by 2. So we need to draw the relation pattern of 4 isotropic elements, space lambda by 2 apart. Now we have marked a point A exactly at the midpoint of 1 and 2 here. Here also we are marking the point B exactly at the midpoint of 3 and 4 here. So exactly at the midpoint the length will be lambda by 4. So exactly at the center the length will be, it is lambda by 4. So for this lambda by 4 and for this lambda by 4 and lambda by 2, the total length becomes lambda here. So here for this A and B separated by lambda, the resultant pattern is given by the unit pattern of A or B multiplied with group pattern of A and B here. Unit pattern of A or B multiplied with the group pattern of A and B here. So the unit pattern of A or B, it is nothing but, what is the unit pattern of A? The unit pattern of A is nothing but the resultant pattern of 1 and 2 here. The unit pattern of A is nothing but, it is the resultant pattern. You can see here 1, 2, 3, 4. 1, 2, 3 and 4. This is lambda by 2, this is lambda by 2 and this is lambda by 2. So we are going to combine these 2 elements as one element. These 2 elements as one element here. And here the total distance is lambda here. So this is the center lambda by 4. This is the center. This is A and this is B. So the resultant pattern, it is given by unit pattern of A or B multiplied with group pattern of A and B. So this is equal to, what is the unit pattern of A? It is a combination of 1 and 2. That is, here the unit pattern of A is equal to the resultant pattern of 1 and 2 separated by with lambda by 2, separated with lambda by 2 spacing. So the resultant pattern of 1 and 2 is nothing but, we will get this like this, the relation pattern. And similarly the group pattern of A and B, it is separated by lambda, whose separation is lambda. So you will get the separation as the value of a group pattern of lambda, that is whose separation is lambda, the spacing between the elements is lambda. You will get the relation pattern as like this. That means the nulls are in the direction of 60, 60 and 120. So we are going to multiply this with this. That is, unit pattern multiplied with group pattern gives rise to resultant pattern. So here we can write the first one, the unit pattern. For the unit pattern we can write as, first indicate the nulls here, 0 degrees, this is 180 degrees. 2 elements separated by lambda by 2. If we simplify, we will get the nulls as 0 and 180. And the radiation is, it is 90 degrees. This is 90 and this is 180. So multiplied with the group pattern. So what is the group pattern here? The group pattern is, we are having, first you indicate the nulls here. These are nulls here, 60 degrees. This is 120 degrees. This is 180 degrees. And this is 0 degrees. These are known as nulls here. So this is maxima and this is maxima. So maxima multiplied with maxima gives rise to a bigger radiation pattern. Indicate nulls here, 60. This is 120. This is 0 and this is 180 degrees. This is 180 degrees. So this is known as the resultant pattern. This is known as the resultant pattern. So this is how to draw the relation pattern of 4 elements. So similarly, the same can be applied for 8 elements also. So this is the relation pattern produced by two elements separated with lambda. Suppose there are two elements separated with lambda, so we will get this radiation pattern. So this is the radiation pattern here, the resultant radiation pattern. We can draw by means of sketch also. So for 8 elements, so for 8 elements also the same technique here. 1, 2, 3, 4, 5, 6, 7, 8. All are separated with the lambda by 2. All are separated with the lambda by 2. Let us combine these 4 elements as 1 unit here. 1, 2, 3, 4 elements as 1 unit. And 5, 6, 7, 8 as 1 unit. Join these two. This is A and this is B. So the total length is, it is 2 lambda here. So why? Because up to here, if you draw a dotted line, so you will get here lambda by 2 plus lambda by 4 here. And here also you combine here. So here lambda by 2 and lambda by 4. So total length is 2 lambda. Now what is the resultant pattern? Unit pattern of A multiplied with, or B multiplied with group pattern of A and B separated with 2 lambda. Now what is unit pattern of A? Unit pattern of A is equal to the resultant pattern of 1, 2, 3 and 4 elements separated with lambda by 2. So here, so if we want to draw the radiation pattern of 8 elements, we should know the radiation pattern of 4 elements whose separation of elements between is lambda by 2. So if we want to draw the radiation pattern of 4 elements, we should know the radiation pattern of 2 elements. So like this, we can extend the same concept for 16 and 32 also. So this is the radiation pattern of 2 lambda here. And this is the separation of individual element of lambda by 2 here. So we multiply these two, you will get this radiation pattern. So for 2 lambda radiation pattern, these are the nulls here, 48, 60 and 76. And similarly, we can try for the broadside array. So the broadside array of identical antenna consists of 4 isotopic radiators separated by lambda by 2. Find radiation field in a plane containing line of array showing directions of maxima and minima, and also find the directivity. Similarly, as how we have determined the value of E is equal to 2 E naught cos I by 2. Here the separation is lambda by 2. So we are going to find out the direction of maxima and minima here. So psi is equal to beta t cos theta plus alpha, we know. And for broadside array, theta will be in the direction of 90 or 270. This is a maxima. So the pattern maxima equation is given as Et is equal to E naught sin n psi by 2 plus sin psi by 2. And it is maximum sin n psi by 2 is equal to 1. So for this, the mathematical trigonometric expression solution, the trigonometric solution for this function is given as n psi by 2 is equal to plus or minus 2n plus 1 into pi by 2 here. Substitute n is equal to 1, 2, 3, 4. So n represents the major lobe maxima. And small n is number of sources in an array. Number of elements in an array, small n. And number of lobes we indicate as capital N here. So number of major lobes or minor lobes, it is a use symbol n here. What is psi here? Psi is beta t cos theta plus alpha. As we are going to find out the major lobe maxima, hence we are given the specification as theta max min here. So the minor lobe maxima. So minor lobe maxima means this is known as major lobe maxima, and these are known as minor lobe maxima. So this is n is equal to 1 here. This is n is equal to 2. So minor lobe maxima. We are going to indicate by the term theta max of min here plus alpha. So plus or minus 2 plus 1 into pi by n. Let us substitute beta as from this equation. If you simplify, you will get this value, minor lobe maximum value. And our case is 4 elements we are having. So d is the spacing, n is the number of sources. The n is so taken as 4 here. So beta is 2 pi by lambda, and d is the spacing given as lambda by 2. So let us substitute these 3 values here and find out the values of minor lobe maximum. So this is the case we are having when the problem given data n is equal to 4, d is equal to lambda by 2. Let us substitute. Let us assume n is equal to 1 here, first minor lobe maxima. You will get plus or minus 0.75 here. So these are known as the minor lobe maxima. It means that this is the major lobe maxima, and this is 0, and this is 41, and this is 138. 138, and this is minus 41, and this is minus 138. So these are known as minor lobe maxima. These are known as minor lobe maxima in the direction of 41.4 here. So like this, we can draw the radiation pattern for a broadside array here. You can see here 41.4, 61, 60 minor lobe maxima. And, these are known as minor lobe minima here. These are minor lobe maxima here. These are known as nulls. Null means there is no radiation pattern in the direction of 60 degrees and 120 degrees. Hence the name is given as null. These nulls are also known as minor lobe minima. Minor lobe minima, we call it as nulls here. So we are having here 41.4, 41.4, 138.6, minus 138.6. Right? So these are known as the minor lobe maxima. So how to find out the pattern minima here? So we can also equate this equation, find out from the trigonometric solution for this. The minimum value is 0 for sine function. From this we can write psi as 2n pi by n, where psi is equal to beta d cos theta plus min here. Beta d cos theta plus alpha here. So we are going to find out the minor lobe minima. So hence the name is given as theta min or minor. Or find out this value. And substitute n is equal to 4 here. This is 2 pi by lambda and d is equal to lambda by 2 here. So after finding these values, you will get substitute the given specifications of the problem here. You will get cos of plus or minus 1 by 2. So this is known as a 60 and 120 here. Plus or minus 60, plus or minus 120. There will be no radiation in this direction of 60 and 120. Also 0 and 180. If substitute n is equal to 2, you will get 0 and 180. Substitute the value of n is equal to 2 here in the above equation. And if you simplify, you will get 0 and 180. So 0, 180, 60 and 120, these are known as nulls. So the final radiation pattern is this. A broadside array operating at 100 centimeters wavelength consists of 4 half-wave dipoles spaced 50 centimeters. Each element carries radio frequency current in the same phase and magnitude of 0.5 amps. Calculate the radiated power. So given the lambda value is 100 centimeters and n is equal to number of sources is 4 and I is given as 0.5 amps. So RR is equal to 80 pi square dl by lambda whole square we know. But actually in the given problem it is given as half-wave dipole antenna. Hence we can ignore the value of lambda here. So we can ignore the value of lambda here. Just we can write directly as the radiation resistance of half-wave dipole antenna is 73 ohms here. And here we are know that P is equal to Vi here. What is V? V is equal to IR into I. So this is equal to I square into R. So from this equation we can write I square RR here. So I square RR means it is radiation resistance. The radiation resistance is given as 73 ohms and I is given as 0.5. So this is the power radiated. This is the power radiated is 18.25 watts here. And here this is for each individual element. As there are 4 individual elements, you can multiply this 18.25 into 4 here. 18.25 into 4. So one individual element will radiate a power of 18.25 watts. And as there are 4 number of elements, so 4 into 18.25, you will get 73 watts here. 73 watts here. So with this we close our session. For references, you can refer the antennas wave propagation E.A. Bakshi. Also the K.D. Prasad antenna waves and propagation. And for more number of critical problem thinking, and for more number of problems and definitions, we can refer Balanis also, the textbook Balanis, and also John D. Cross antennas and waves and propagation. So let us close our session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.